video, basic concepts about phasors will be introduced. Being able to work with phasors will assist you in analyzing AC circuits that contain both resistive and reactive components.
You'll see how phasor diagrams are constructed and how phase angles relate to sine waves. The Pythagorean theorem will be presented. You'll see how right triangle relationships can be used to analyze AC sine waves that are 90 degrees out of phase.
Let's get started by learning to read phasor diagrams, which is an important skill for a technician to have. Phasors are a graphic way to represent AC.
From your previous studies, you've learned that a sine wave is a graphic representation of AC. You've seen how a sine wave indicates frequency, peak, and instantaneous value. A phasor diagram is also a graphic tool. It is used to compare the interactions of multiple voltage and/or current waves within the same circuit.
Let's see what a phasor diagram looks like by constructing one using the standard coordinate system.
Start with a sheet of graph paper. Draw a vertical line to represent the y-axis. Then draw a horizontal line to intersect it at a right angle. This is the x-axis. The point where they intersect is called the origin.
No doubt you've used this type of graph before to depict waveforms. Now let's see how it can be turned into a phasor diagram.
Start by thinking of the graph in terms of degrees. A circle has 360 degrees. Let's see how these degrees can be plotted. The x-axis, moving from the origin to the right, can be designated as 0 degrees. The y-axis, from the origin moving upwards, becomes 90 degrees. The x-axis, from the origin to the left, is labeled 180 degrees. And the y-axis, moving from the origin downward, is designated 270 degrees. Coming back around to the x-axis from the origin and moving to the right completes 360 degrees.
A phasor is simply a line that is drawn from the origin as an arrow. It can point in any direction. Two characteristics of the arrow will determine how the phasor is interpreted. One is the length of the phasor. The length of a phasor represents the maximum amplitude or peak of the AC voltage or current wave. The second characteristic to notice about a phasor is the angle at which it's drawn, known as the phase angle. A phase angle is always formed in respect to the 0-degree segment of the x-axis and is labeled using the Greek letter theta.
Let's try reading some example phasors.
Here is a phasor with a length of 3 and an angle of 45 degrees.
Here's another phasor with a length of 5 and an angle of 90 degrees.
In this third example is a phasor with a length of 4 and an angle of 180 degrees.
And finally, here's one whose length is 1.5 and whose phase angle is minus 45 degrees. Remember that the degrees of rotation associated with a sine wave are determined by the rotation of a generator's armature, which creates the alternating wave.
Let's see how a phasor's angle can correspond to any degree point on the sine wave. To do this, they'll be plotted side by side to see how each mirrors the other. The phasor will be on the left and the sine wave on the right.
Both types of graphic representations begin at 0 degrees. Both the sine wave and the phasor move upward through 45 degrees to 90 degrees. Notice that the length of the phasor is equal to the peak value of the sine wave at this point.
The sine wave and the phasor descend through 135 degrees to 180 degrees at the baseline. The phasor moves to the same degree point, representing 1/2 of a full revolution.
The sine wave and the phasor then continue by descending through 225 degrees to their negative peak at 270 degrees. The phasor reflects these degree changes. Notice again that the length of the phasor is equal to the peak value of the sine wave at this point as well.
Finally, the sine wave moves upward toward the baseline, through the 315-degree point, as does the phasor. Both complete one cycle at 360 degrees. Each point on the sine wave can be represented by a phase angle.
You can begin to see how sine waves and phasor diagrams are closely related. Another important aspect of phasors is that their position can represent either a positive angle or a negative angle. Let's see how this is so.
You've already seen how a positive phase angle is measured by moving counterclockwise from the 0-degree x-axis. This direction is used to represent a phasor that leads another. A negative phase angle, on the other hand, is measured clockwise from 0 degrees on the x-axis. It's used to represent a phasor that lags another. If you know one of the phase angles, either the positive or the negative, you can determine the other phase angle by subtracting the known angle from 360 degrees. For example, if the positive phase angle is 225 degrees, then the negative phase angle is calculated by subtracting 225 degrees from 360 degrees. This yields 135 degrees. Since this is a negative phase angle, the answer will be minus 135 degrees.
You've been shown several characteristics of phasors. Now let's see how useful a phasor diagram can be for showing the relationship between two AC signals.
Here are two voltage sine waves. Notice that sine wave A at 5 volts is leading sine wave B at 10 volts by 45 degrees. Let's construct the phasor diagram, which will represent the peaks and phase relationship between these two sine waves. When creating a phasor diagram, it's important to establish the reference phasor first. The reference phasor is determined by the sine wave that begins at 0 degrees, which in this example is sine wave B. Phasor B, with a peak of 10 volts, is drawn along the horizontal axis from the origin. Because sine wave A, which peaks at 5 volts, is leading wave B by 45 degrees, phasor A is drawn with a length of 5 volts at a 45-degree angle. Don't forget that the length of the phasor is determined by the peak of the sine wave. The phasor diagram is now complete. Phasor A is shown to be leading phasor B by 45 degrees.
Let's plot another example.
Here are two voltage sine waves. Wave A, which peaks at 4 volts, is leading wave B by 90 degrees, which peaks at 3 volts. Let's construct the phasor diagram. Once again, establish the reference phasor. Phasor B is plotted 3 volts long on the horizontal or x-axis at 0 degrees. Phasor A is drawn 4 units long, representing 4 volts. Because it is leading phasor B by 90 degrees, phasor A is drawn along the y-axis from the origin upward. The phasor diagram is now complete.
Now let's do the opposite. Let's plot the sine waves from information given in a phasor diagram.
Notice in this diagram that phasor B, which peaks at 1 volt, lags phasor A at 3 volts by 135 degrees. The reference phasor, phasor B, should be drawn from 0 degrees. Remember, it peaks at 1 volt. Because the position of phasor A indicates a lead of 135 degrees, it is drawn at this point, rising to a maximum amplitude of 3 volts. The two sine waves have now been successfully reconstructed based on the information given in the phasor diagram.
Stop the program and complete activity number 1. When finished, continue watching the program.